Go ahead and pause the video and try these atomic structure questions on your own. Restart when you have an answer for each to see what you remember about atomic structure. So the first one, when you're looking for number of protons, we're looking for the atomic number of iron, which is 26. Remember that this number here is the mass number. So to get number of neutrons, we're going to do mass minus atomic number, and the atomic number for potassium is 19. So we have 20 neutrons. On this next one, calcium's atomic number is 20, so that's number of protons. And to get neutrons, we're going to do mass minus atomic number, so 22 neutrons. For the last one, my protons never change, so the atomic number of nitrogen is 7. And if it's a -3, that means you gained 3 electrons. So you have 10 electrons. Notice I have more negative than positive, so that gives me an overall negative charge. In Unit 1, we're going to be talking about moles, molar mass, mass spectrometry, the composition of pure substances versus mixtures, electron configuration, PES diagrams, trends, and how valence electrons affects properties. So the first thing will be moles. On the formula chart, you have moles is equal to moles over molar mass. And remember, Avogadro's number is also listed on there, which is 6.022 times 10 to the 23rd. That's the number of particles in a mole. So here are your 3 mole conversions that you should know. So 1 mole is equal to so many grams from the periodic table. 1 mole is equal to 22.4 liters, but that's only of a gas at STP. If it's not a gas or at STP, you cannot use 22.4 liters. And finally, 1 mole is equal to 6.022 times 10 to the 23rd particles. Those particles can be atoms or molecules or formula units. Go ahead and pause the video and try these 2 on your own. The first one, you can use a calculator. The second one, you should not be using a calculator. So try solving it without a calculator. For the first one, we have 35.9 grams of NO2. Step 1 is I need to convert my grams to moles. There's 1 mole is so many grams. From the periodic table, that's 46.01 grams. And then I can convert my moles to molecules. For every 1 mole, there's Avogadro's number of molecules. So multiplying and dividing, I get 4.70 times 10 to the 23rd molecules. For this second problem, we started with 88 grams of C3H8. I'm going to have my grams of C3H8. Because we don't have a calculator, we're going to go and round sum. So each carbon is 12. 12 times 3 is 36. Plus 8 is going to give me 44. So 44 grams for every 1 mole of C3H8. But we want moles of carbon, not moles of C3H8. So for every 1 mole of C3H8, I have 3 moles of carbon, since there's 3 carbons in the molecule. To solve without a calculator, we're going to reduce. So 44 and 88, that goes 1 and 2. So I get 6 moles or 6.0 moles of carbon as my final answer. This question says, which would have the greatest mass of chlorine? For this one, you need to remember that mass percent is mass, in this case, mass of chlorine, over total mass. To find the greatest mass of chlorine, it would technically be 6.3 grams times my mass of chlorine over total mass. Because these all have 6.3 grams, and they all have 1 chlorine, really I'm just looking for the smallest molar mass. The smallest molar mass would give me the biggest mass per total mass, or the biggest percent chlorine. So I want the greatest percent chlorine, which would be the one that has the smallest overall molar mass. So lithium chloride would have the greatest mass of chlorine. And then the heaviest, or rubidium chloride, would have the smallest mass of chlorine because it has the smallest percent by mass of chlorine. You'll also need to be able to read and interpret mass spec data. Before we can interpret mass spec data, remember that the atomic number, like we had mentioned in the warm-up, tells you the number of protons. It's the one thing that makes one element different from another element. Neutrons and electrons can change, but protons cannot change. If the protons change, the element is going to change. When the number of neutrons change, that means it's an isotope. So isotopes have the same number of protons, but different numbers of neutrons. So here you can see hydrogen has 3 isotopes listed. Hydrogen 1 doesn't have any neutrons. Hydrogen 2 has 1 neutron, and hydrogen 3 has 2 neutrons, but they all have 1 proton. Because they have different numbers of neutrons, they're going to have different masses, which is that top number. To calculate the average atomic mass, it's a weighted average of all the masses of isotopes of a particular element. So you do mass times percent plus mass times percent plus mass times percent, but your percent would need to be in decimal form. So if it was 40% abundant, we would use 0.40. Either that or you divide by 100 at the very end. This average atomic mass is what's located on the periodic table. So how we would do a mass spec graph, first thing that you may have to interpret is how many isotopes this graph is representing. Every peak is an isotope. So there's 1, 2, 3, 4, 5 isotopes. The most abundant is going to be the tallest. So here's relative abundance. This one is 50% abundant. And we also know that the average mass has to be between 74 and 80 because you can't have an average outside of the range of the smallest and largest isotopes. So go ahead and pause the video and answer this question, restarting when you are done. On this problem, we're looking to see which statement is false. So the answer is D, because it's talking about protons. All of these peaks are coming from the same element, which means they all have to have the same number of protons. Peak C is more abundant, is the most abundant because it's the tallest peak. There are 7 isotopes, 1, 2, 3, 4, 5, 6, 7. And we can't tell number of electrons, but because it says atoms, the atoms have to have the same number of electrons. Otherwise, it would be an ion. So looking at the periodic table, determine which element you think this is. You would need to look at the average atomic masses. Zirconium has an average mass of 91, 95.9, 243, and 252. The mass, we said, has to be between 92 and 100. Why people choose C and D is they look at the atomic number, but we're not looking at the atomic number. We should be looking at the mass numbers, which are on the bottom. So the only answer choice that's in that range would be B. Go ahead and pause the video and answer this one. Now we're looking to see which peak comes from the atom with the greatest number of neutrons. Well, the greatest neutrons would have the largest mass, and the largest mass is 100. So the answer is D. One more mass spec question. Go ahead and pause the video and answer this one. Restart when you are done. So for this one, we know that the sample couldn't have any NB because it says that NB has only one stable isotope with a mass of 93. So if there was any NB, then there would be a peak here at 93, which there's not. So D would be the best explanation on why we only have zirconium in this sample. We can't tell any of the other answers based on a mass spec graph. So for this next section, we're looking at empirical and molecular formulas. An empirical formula is the simplest whole number ratio of atoms in a compound, while the molecular formula is the true formula. It's usually a multiple of the empirical, but sometimes the empirical and molecular can be the same. So glucose has this for the molecular formula, but can be reduced by 6 to give the empirical formula. To find the empirical formula, we're going to first convert the mass or percent to moles. If they give you moles, then you could skip step 1. Step 2 is divide all elements by the smallest number of moles. And finally, multiply all elements by a number until all of them are whole numbers. So convert to moles, divide by smallest, multiply till whole. On this problem, we said no calculator. So step 1 is we need to convert them to moles. So 14 grams of nitrogen. And I'm trying to find out how many nitrogen and how many oxygen are in this compound. So although nitrogen is diatomic, we don't care that it's diatomic because in this problem, it wouldn't be diatomic because it's not by itself, it's in a compound. So we just look on the periodic table and see that nitrogen has a mass of 14. So for every 1 mole of nitrogen, I have 14 grams. For oxygen, same thing. It's just regular O, not O2, which means it has a mass of 16. Well, 14 divided by 14 is 1 mole of nitrogen, and 32 divided by 16 is 2 moles of oxygen. Then I would divide by smallest, which in this case is 1, and I don't need to multiply because I'm at whole numbers already. So this tells me that I have 1 N and 2 O's, so NO2. Go ahead and pause the video and try this one on your own. Again, try solving without a calculator. Restart once you have an answer. So for this one, we are 21%, so that's 21 grams of nitrogen. My nitrogen is 14 grams for every 1 mole. And X is 100 minus 21, or 79. So 79 grams of X. And they tell me the molar mass of X is 79 grams. Very convenient there. So 79 and 79 is 1 mole of X. And here, both of these numbers are divisible by 7. So 7 goes into 14 2 times, and 7 goes into 21 3 times. So 3 over 2 is 1.5 moles of nitrogen. I'm going to divide by smallest, which is going to give me the same thing. And finally, I need to multiply till whole. Well, 1.5 times 2 will give me a whole number of 3, and times 2 gives me a 2. So I have X2 in 3. I look at my answer choices, and I have something that matches that. And one more empirical. So I'm going to try this last one again without a calculator. So this one, to simplify the problem, you're given moles since you don't have a calculator. So step 1 was convert to moles. That's done. So now I'm going to divide by smallest. Well, 0.65 is my smallest, so that's going to give me a 1. 0.65 times 2 is 1.3. So if I divide by 2, or 0.65, that's going to give me 2 then. And 2.6 is double 1.3. So if this was a 2, then I know this one has to be a 4. I don't need to multiply because I have whole numbers for everything. So that's 2 NAs, 1 TE, and 4 O's, or B. You also need to be able to recognize mixtures and how we can use elemental analysis to determine if a substance is pure or not. Impurities in a substance can change the percent composition by mass. It can give you a greater percent by mass or smaller mass percent depending on the impurity's molar masses. If more of a certain element is added from an impurity, then the percent mass of that element will increase and vice versa. When heating a hydrate, or really any substance that you filtered with water, the substance is heated several times to ensure the water is driven off. Then you are simply left with the pure substance and no excess water. The main lab that we do to determine if a substance is impure or pure is react it with another substance and get a precipitate. We can measure the mass of that precipitate, and that we know is pure, and we can compare its percent composition with the mass that we started with to see if we had a pure substance to begin with or if it had impurities in it. So we usually use gravimetric analysis for impurities. So go ahead and read through this problem, restart when you've read through it, and have a guess on your answer. So this is what I was talking about a second ago. We have a 10-gram sample of a white powder. It could be barium chloride. It may not be barium chloride. We're going to add excess sodium sulfate to it, which causes a precipitate to form. The student filters the barium sulfate, rinses it, dries it, until the mass is constant. We would not be testing to see if sodium sulfate is pure because sodium sulfate is in excess, which means if it wasn't pure, we wouldn't know because we're using more than we needed to for the problem. We do want to know if barium chloride is pure or not because all of our barium chloride reacted, so the percent of barium sulfate, or the percent of barium in barium sulfate, can be tied back to the percent of barium in our starting barium chloride to see is the substance pure or not. For molar solubility, we'd have to have saturated solutions, which we won't have a saturated solution if we're just mixing two amounts without making it saturated. So here we have a jar labeled NaCl, and we have some information, and we want to know what would be most helpful in determining whether the NaCl is pure or not. Well, just knowing the mass of NaCl isn't going to help us determine if it's pure because I could easily have more mass or less mass, and mass changes. So mass is an extensive property, so that's not going to help us. The color also really isn't going to help us unless it was mixed with something that was, let's say, green. Then we could see the specks of green in the substance, so we could easily tell that it was not pure. But there's lots of white substances, and it'd be hard to see otherwise. While knowing the mass percent of sodium would help us, because if we were to react it with another substance, and we could test its mass percent and see if we had gotten all of the sodium or if our mass percent was less than what we would expect it to be. Like in this case, this was all of our data. If we did the mass percent of sodium in sodium chloride, we would have the mass of sodium over mass of sodium chloride. The mass percent should be 39.34. Notice it is less than that, meaning that we must have had an impurity in our sample. Atomic structure and electron configuration. Notice that you will not have to do quantum numbers And it's not on this one, but you also don't have to do the exceptions to electron configurations. Aufbau's principle says that as protons are added to the nucleus, electrons are added to the orbitals at the lowest energy first. So it's got to start at 1s, then go to 2s. It can't just start at 5s. You do not need to know the names, but you should be familiar with what the principles stand for and the rules that follow. Hund's rule says electrons don't pair up until they have to. So when it's filling the 2p, it would put 1 in each p orbital, then it would go back and fill them, because these are all degenerate, meaning equal energy. So it'd fill the 1s, then the 2s, and then 1 in each p before following up, pairing them up. Pauli's exclusion principle says that no two electrons can have the same set of quantum numbers. What that simply means is you can't have two arrows going up, nor can you have 3 electrons in any of these orbitals, because then 2 would be exactly the same. So in other words, electrons have to have opposite spins, and you can only have 2 electrons, no more than 2 electrons in any orbital. When doing electron configuration, remember that this was your S block, and it was the same as the periods. This was the P block, and it was the same as the period as well. The D's start in the 4th period, and they're always 1 less than the period. P's can hold up to 6. D's can hold up to 10. And then the F's are going to be 2 less than the period number. So they fit in the 6th period, and that's 4F and then 5F. And those go all the way to 14. This question says, which of the following is an excited state? An excited state means something was skipped. It's not following Aufbau's principle. Something was skipped because it went to an excited state. It's not going to be able to stay in that excited state. It's going to come back down and releasing energy, but currently something is skipped. So go ahead and pause the video and look at those electron configurations and see which one is skipped currently. So C is our answer because it went 1s, then 2s, then 2p, then 3s, and it's missing the 3p6 before moving on to 4s. Sometimes they're just out of order. Out of order doesn't mean that something was skipped. Like in A, it looks like we skipped the 4s, but it's just on the end, so all the 3s are listed together. Be careful on our ions down here. Remember, for our ions, if it's positive, it lost an electron, and if it's negative, it gains an electron. You may want to write the atom configuration and then add or remove electrons from there. Go ahead and pause the video and try these 5. Restart when you have these 5 done. So for sodium ion, this is sodium atom, but because it was a positive one, it's going to lose the 3s1. So fluorine was 1s2, 2s2, 2p5, but because it's a negative one, it's going to gain an electron and have it in 2p6. Notice these two have the same electron configuration, which in a few minutes we're going to call isoelectronic, meaning they have the same number of electrons. So this is what you should have gotten for iron atom, but we want to pay attention to the numbers in front. We've got the first ring, the second energy level, the third energy level, and the fourth energy level. We've got to lose electrons from the outer ring first because those are farther from the nucleus. So I'm going to lose from the fourth ring, but that was only 2, so then I can lose 1 from the 3d, giving me 3d5. So my final electron configuration should be that. So now let's look at some shorthand. Let's look at the first one together. So uranium, when we're doing shorthand, we're going to choose the noble gas that comes before it, which is radon. and then follow that atomic number. After radon, we're going to go to 7s2. And then after 7s2, then we actually go to 6d1 before going down to the F's. And the F's are 2 less, so that's 5f3. If you go all the way through the D's, then you could come back to the D's and put them either spot before or after the F's. Go ahead and pause the video and try these last ones on your own. Restart when you're done. So for lead, you could have said xenon 6s2, 5d1, 4f14, 5d9, as long as your 5d's added up to 10, and then my 6p2. I could have also reversed these. It doesn't matter the order as long as you have those as your sublevels listed. The next three were ions. So copper, we have argon. It loses the 2,4s, and we're only left with 3d9. For tin, we have krypton, and then krypton loses the 5s2, and it loses its 5p2. So we only have krypton and then 4d10. And then finally bromine, because it's gaining electrons, it's got the 4s2, the 3d10, and then the 4p6. PES, you need to be able to understand the relationship between PES and electron configuration and the interactions between the electrons and the nucleus. So with that relationship or interactions, we have Coulomb's law. So the force of attraction is equal to Coulomb's constant times Q1, Q2, which are charges, over the distance of separation. You don't have to be able to solve Coulomb's law. You just need to know that it has to do with charges and distance. And all explanation should always come back to charge and distance and be specific. So for instance, larger nuclear charges will lead to a greater attraction with the valence electrons and the nucleus. Or if we have a smaller distance between the nucleus and valence electrons due to less energy levels, will also lead to a greater attraction. So it'll lead to a greater attraction with the nucleus and those valence electrons. So this is a PES diagram. To read them, you find the largest number on the bottom, or the x-axis, because that's the energy needed to remove that electron. So we have 100, we have 6, 3, and 0.5. The one that requires the most energy to remove is the closest to the nucleus. So this is the 1s2 peak. I say 1s2 because it has 2 electrons. The height of the peak has to do with how many electrons are in that sublevel. After the 1s, I would go to the 2s because that would be the next closest to the nucleus, requiring the most energy to remove. After 2s is the 2p. Notice that I've got 6 in this one, and it's about 3 times as high. After the 2p is 3s, and notice this peak is half the height. It only has 1 electron, so that's 3s1. So that means this corresponds to sodium. Go ahead and pause the video and try figuring out which element this one belongs to. Restart when you're done. When labeling your peaks, make sure you label the peaks and don't just count the numbers on the top, because doubtful the AP test will actually give you these numbers. So this was our highest in energy, so that's 1s2, 2s2, 2p6. And these are also on different axes because for the scale, this is 100 to 500, this is 10 to 100. Instead of having a long line with little breaks in the middle of the x-axis for large jumps in energy, they just put them on different lines sometimes. After 2p6, we have 3s2, 3p6, After 3p6 should be 4s2. But notice this only has 1. So that's not 4s2. My 4s2 is actually right here. And then after 4s is actually 3d. So that's 3d1. All of the 3's are going to be roughly the same in energy, or pretty similar in energy, because they're all equal distance from the nucleus. They're all in the third ring. That's why I lose this 4s before I can lose, let's say, the 3d. So this one corresponds to scandium, because that is 3d1. Okay, go ahead and pause the video and account for the differences in ionization energy with nitrogen, which is on the left, and oxygen on the right here. So first, R1s. Oxygen has more energy to remove a 1s than nitrogen does. That makes sense. Oxygen is further to the right. We'll be talking about trends in a minute, but oxygen has more protons. If it has more protons, it's got a greater charge. So oxygen requires more energy to remove an electron from its 1s and 2s orbitals. But if we look a little closer, the 2p is actually harder to remove from nitrogen than oxygen, even though oxygen has more electrons. If we look at nitrogen's 2p, it has 3 electrons, while oxygen's 2p has 4 electrons. So the answer comes from here, where we have 2 electrons paired together. That would be the only reason why something that has more protons is easier to remove, is there must be some repulsions going on. So oxygen, 2p electrons have 1 paired electron, which has more repulsions than oxygen's 2p, that doesn't have any paired 2p electrons, which is why oxygen's 2p requires less energy to remove. You also could have stated that oxygen has a higher peak for this one because it's got more electrons in that 2p than nitrogen does. Go ahead and pause the video and answer question A. When you finish with A, then restart the video. So fluorine was the pink one, and boron is blue. So it says, why are all of the pink peaks further to the left than boron? Well, remember that this is energy to remove an electron. And fluorine has a greater effective nuclear charge because fluorine has 9 protons while boron only has 5 protons. More protons is a greater effective nuclear charge, meaning the electrons and all the subshells are going to be held together more tightly. And then B, go ahead and solve B, restart when you're done. So it says, why is there one peak in fluorine that is so much taller than the others? Well, all these other peaks, that's my 1s2, 2s2, this is 2p5. And then for boron, that's 1s2, 2s2, 2p1. So fluorine has 5 electrons in the 2p, while boron only has 1 electron in its 2p. So fluorine's 2p peak is much higher than boron's 2p, and all the other peaks are 1s or 2s, which causes them to only have 2 electrons. And remember, height has to do with number of electrons. Go ahead and solve these 4 and restart when you have these 4 done. So the first question was just the full electron configuration for sulfur. So you had to have 1s2, 2s2, 2p6, 3s2, 3p4. You had to do it starting with 1s. B says label each peak. So that's 1s2, 2s2, 2p6, 3s2, 3p6. 3p4. Next, on the spectrum, sketch the relative locations and correct peak heights for aluminum. Well, aluminum has less protons, so sulfur has 16 protons. So anytime it says Z equals, that's your protons. So sulfur has 13 protons, while aluminum only has 13 protons. Because aluminum has less protons, it would be less held, its electrons would be held less tightly to the nucleus, so they should be further to the right. But height-wise, they should be the same height. For all of them except this last one, aluminum only has one electron in its 3p, so it should be half the height of any of the ones that were S's. And finally, our last question says, draw a circle around sulfur's peak whose energy is equal to the first ionization energy. In other words, which peak would have an electron removed if I were to remove one electron? Well, I would remove it from the outer, not the one closest to the nucleus, because 3p requires the least amount of energy to remove an electron from. So that peak is the peak that sulfur would lose an electron from if it lost an electron. Go ahead and pause the video and answer these 4 questions on your own. Restart when you are done. This will be our last PES question. So when given a PES question, the first thing you want to do is label everything. So that's 1s2, 2s2, 2p6, 3s. It's half the height, so 3s1. It should be filling each of them before moving on, so that's how I know it's 2p6 and not 2p4 or 5 or any other number. So it says which one represents the 2s. Well, I've already labeled everything, so that becomes an easy question of just B. The next one says, well, which one is valence electrons? Valence electrons are my outermost electrons, so that would be D. Which one is closest to the nucleus? That would require the most energy to remove, which is also in the first ring, so that would be A. And the last one says, which one contains 6 electrons? Well, that would be my one that's the tallest out of all these, or C. You also need to know your trends: ionization energy, atomic and ionic radius, electron affinity, electronegativity, and how the periodic table is organized. So remember, we have periods going across the periodic table. So this is period 3. And then we have groups going down. Periods have the same number of energy levels. So this element and this element have the same number of energy levels. While groups, or going down, have the same number of valence electrons. Valence electrons give us our properties. So if they're in the same group, they should have similar properties. You may need to know the name of one of the groups. Maybe it'll ask something about one of the groups. Make sure you know that this column is the noble gases. They're the least reactive. The column next to it is the halogens. This first column is the alkali metals, and they are the most reactive metals, just as the halogens are the most reactive metals. The second column is the alkaline earth metals. And finally, this middle section is the transition metals. So this middle section in here are the transition metals. Ionization energy is the energy required to remove an electron from an atom or an ion. First ionization energy is the energy to remove one electron, while the second ionization energy is the energy to remove a second electron, which is always much higher than the first, because the remaining electrons are going to be closer to the nucleus due to less repulsions. So ionization energies increase as we go up and to the right. Notice my cesium is 382 and then helium 2377. There's some exceptions to some of these, but in general, as I go up and to the right, ionization increases. Make sure you know why. You cannot say because it's further up or further to the right. So as you go up, ionization energy increases because there's less energy levels of electrons. So electrons are going to be closer to the nucleus because they have a smaller distance and they have less electron-electron repulsions. Or as I go down, there's more energy levels, more repulsion, so the electrons are further from the nucleus. And as I go right across the period, the elements have the same number of energy levels, but more protons, and thus the element has a greater effective nuclear charge. It's able to attract those valence electrons much more effectively, pulling them in, making it harder or requiring more energy to remove one. Make sure you have those reasons down because this is for ionization energy, but it's also for atomic radius and for electronegativity. Anytime it's talking about any of the trends besides ionic radius, these are our main two reasons. Up, down, you should be talking about energy levels and electron-electron repulsions. And as we go either left or right, we should be talking about same number of energy levels, but that effective nuclear charge, which has to do with the number of protons in the nucleus, is the thing differing. Another way that you can see an ionization energy question asked is given an ionization energy table like this one and asking which element does this correspond to, or how many valence electrons does this element have, or what would be a most probable charge of said element. So to answer this question, you're looking for the biggest jump in energy. So from first to second, it increases, but it doesn't increase that much. It barely doubles. Or it doesn't even double, actually. And then from second to third is a huge increase. So that would be my biggest jump, which means these must be valence electrons, and this must be a core electron. Core electrons are closer to the nucleus, therefore they require more energy to remove. So for instance, in this case, I've removed one electron. That was my first ionization energy. I've removed a second electron. Notice that this third electron is going to be much closer to the nucleus, so that's why it requires way more energy to remove. So I'm looking for something that has two valence electrons, which would be beryllium. Electron affinity is the energy change associated with the addition of an electron to an atom. It increases as you go up a group and to the right. And when I say increases, it becomes more exothermic. More energy is released because electron affinity is the energy released when an atom gains an electron. The more energy you give it off, the more stable it is because you'd have to put that much energy into it to remove an electron. And electronegativity is the ability to attract electrons. It also increases as you go up and to the right for the same reasons we listed a few minutes ago. So fluorine is generally the most electronegative element. And finally, atomic radius is the distance between the radii of two atoms of an element. So valence electrons are going to be drawn closer to the nucleus, decreasing the size of the atom as you go across the period because we have more protons. And as I go down, I have more occupied energy levels of electrons. Therefore, the atom is able to, or the valence electrons are able to go out further than they would if I had less energy levels, making the radius larger. So here's my trend. It gets bigger as I go left and as I go down. Remember that we cannot say because left and down. As I go down, I have more energy levels, and as I go left, I have less protons in that nucleus. So same reasons as before. Earlier, we talked about isoelectronic. We said that it was the same number of electrons. So isoelectronic, a group of ions all containing the same number of electrons. All of these have 10 electrons, but it's the protons that are different. Oxygen has 8 protons, fluorine 9, sodium 11, 12, and 13. Because aluminum has more protons, it would have the smallest atomic radius. Because more protons has a greater attraction for the electrons, making the overall size smaller. While oxygen has the least amount of protons, so it doesn't have a very effective nuclear charge, and so it would be the largest radius. So pause the video and see which one would have a greater radius and explain why. Restart and see if your explanation is fully correct. So first off, if you said P-3, you are correct. The first thing you wanted to do was list out your protons and electrons for each of those. So off to the side, I had calcium and I had my phosphorus. I have my 20 protons, 15 protons, 18 electrons, and 18 electrons. So these are isoelectronic. They both have 18 electrons, so make sure you compare and contrast. They're the same by having 18 electrons, but calcium ion has 20 protons, while P-3 has only 15 protons. Since calcium has a greater effective nuclear charge, the valence electrons in calcium will be attracted to the nucleus more, making calcium plus 2 smaller. Also, make sure that you actually answered the question. Start with the answer and then the explanation. Sometimes people don't actually answer the question on the AP test. All right, go ahead and try that top one. Restart when you're done. Again, try having a full, complete answer. So on this one, if you said Cu plus 2, you are correct. So they both had 29 protons, but copper plus 1 has 28 electrons, and copper plus 2 has 27 electrons. So they're not isoelectronic, but they're the same element. So again, start with what they have the same, which is 29 protons. But since copper plus 1 has more electrons, it would experience more electron to electron repulsions, leading copper plus 1 to have a lower ionization energy. More repulsions means it's going to be easier to remove an electron, aka require less energy. One more explanation. Go ahead and try this one. Restart when you're done. So for this one, germanium and silicon are in the same column or same family. You could not just say germanium is bigger because it's further down. So first, answer the question, germanium. Silicon's valence electrons are in the 3rd energy level, while germanium's are in the 4th energy level. As germanium's valence electrons are further from the nucleus, it's going to give germanium a larger radius. And the last topic is valence electrons. So the likelihood that two elements will form a chemical bond is determined by the interactions between the valence electrons and the nuclei of those elements. Elements in the same column tend to form similar compounds. And the charges are governed by their location on the periodic table. So go ahead and pause the video and solve this last question. Restart when you're done. So for this one, we're looking for one that's similar to calcium. So I can replace calcium. Well, in order for it to be similar to it, I need the same number of valence electrons, or to be in the same column, and that would be strontium.